Okay, great. So yeah, so we finished with zero knowledge proofs, and today we will start one of the most exciting topics of this course, which is secure multi-party computation. So in secure multi-party computation, you have multiple parties. Maybe let's just stick to two-party computation for now. So I'll start with the example which was given by Andrew Yao, who was the one who invented this notion of secure two-party computation. So the problem is called the Yao's millionaire problem. So we imagine like two millionaires, maybe they are sitting on the beach, they are talking, and they are interested in finding out who is richer without revealing their exact net worth to each other, right? So one option is, of course, they can go to a trusted third party, they can tell their net worth to this third party, and then this party announces the winner. So in cryptography, we don't like trusted third parties. In cryptography, we don't trust anybody except ourselves. And that's what the millionaires would like to do. So, so millionaires would like to run a protocol, a multi-round protocol. They would like to talk back and forth with each other. And at the end of the protocol, they learn who is richer. So essentially, you are trying to compute the greater than equal to function, right? So I have my input x1, you have your input x2, and we are trying to run a protocol which reveals whether or not x1 is greater than or equal to x2. Okay, or maybe the protocol can have three outputs. If x1 is greater than x2, then the winner is p1. If x1 is less than x2, then the winner is p2. And then if neither of these is the case, then we have a tie. So the protocol tells you exactly which of these three cases you are in. And the key requirement is that neither party should learn the exact input, which is the exact net worth of the other party. Okay, so this is a very interesting problem. And what is the connection to zero knowledge? Okay, so in zero knowledge, we were interested in designing a protocol which only reveals whether or not a given statement is true, right? So the verifier, the only thing that the verifier learns is that the statement is true without learning anything else, right? So here we are generalizing a little bit further. So here we specify that the parties learn exactly the outcome of this function and nothing else. Okay, so Yao's millionaire problem is just one instance of secure two-party computation. In general, you can imagine two parties, P1 and P2. Okay. This is called secure two-party computation. It's also, the shorthand is just 2PC. Multi-party computation is MPC. So the private input of P1 is x1 and P2 is x2. There's a public function f. Both of them know what f is and so on. And they would like to run a protocol. At the end of the protocol, both the parties learn f of x1 comma x2. Okay, and maybe, for example, the function is the XOR function. If the function is the XOR function, then given x2 and the function output, I can already compute x1 and vice versa. That's fine. That is not an insecure protocol. Our intuitive definition of understanding is that whatever P2 learns or whatever P1 learns from this protocol can also be computed using the function output alone. And we will try to formalize it a little bit more, but right now at an intuitive level, the only thing the protocol reveals is the output and nothing more. Okay, and this notion was introduced by Andrew Yao. I believe it was in '86, and that was for the case of two-party computation. And this was generalized to the case of multi-party computation by Goldreich, Micali, and Wigderson in 1987. Okay, so it has been over 30 years since this notion came out. And when this notion came out, people thought that secure two-party computation, multi-party computation is never going to be practical. The computers were much slower at that time. The network was slower. The protocols were less efficient. So it was mainly just sort of an intellectual curiosity type of line of research. People who were more practically minded, they never really paid attention to this topic. And all of this changed sometime maybe 10 to 15 years ago. Now, secure two-party and multi-party computation is being used in practice. There are a lot of companies, big tech companies like Google, Facebook, Visa, and so on. They are interested and they are investing heavily in secure two-party and multi-party computation. And one of the reasons for this is sort of the rise of big data. You know, when you have big data, you have big data privacy problems. So here you can imagine X1 and X2. These are like two different data sets. And the parties are trying to compute maybe some sort of machine learning algorithm on these two data sets, right? So as an example, think about multiple hospitals, okay? So maybe there's a clinical trial going on, maybe for the coronavirus vaccine or some treatment or something like that. And there are different hospitals who are treating the patients in different ways, and they have this huge database, what worked and what did not, right? Now, if the hospitals come together and then they combine all this information together, right, we can have very nice information about what works and what doesn't work, right? In medical science, in clinical trials and so on, data is really the name of the game. Data is extremely valuable, and in fact, um, much of the cost of developing any new drug or any new vaccine is really in collecting all this information, in doing the clinical trials. On the other hand, there are several type of laws, like there's HIPAA, which you have to comply with, and so on, which says that you cannot really reveal any personal information, patient information, to anybody else except with the sort of the written permission of the patient, right? So if I have to go to like 1,000 different patients, take their permission, that's probably never going to happen. But the nice thing is secure two-party, secure multi-party computation gives you sort of a framework to solve this problem, right? Different hospitals, they can execute a protocol with each other, right? The input or the database of the ith hospital would be xi, right? And then maybe they are trying to compute what is the success rate of a particular type of therapy for coronavirus patients, right? And then that's a function which takes all the databases as input. And at the end of the protocol, the parties sort of just learn the desired function output without learning any content of the database of the other parties or of the other hospitals, right? Secure multi-party computation can be used by different nations, for example, to share sensitive information with each other. So for example, maybe something like tax evasion, right? Maybe country A is talking to country B and would like to find out if citizens of country A have any bank accounts in country B, right? So country B is just not going to send the entire database of all the bank accounts to country A, but A and B can run sort of a secure two-party computation protocol. The input of A would be the list of its citizens, or rather maybe the list of suspected citizens who are evading taxes. The database of country B would be maybe all the bank accounts held by citizens of country A. And then whenever there's a match, country A learns the function output. So we can imagine a lot of different applications. Now the question is, of course, this is a very nice notion. How do we formalize it? How do we build it? And the cryptographic primitives which we have learned so far, they will be really helpful in the class today. So first, let me try to define what a secure two-party computation is supposed to be. So let me just focus on the case of two parties. Anything which I say can be generalized to the case of multi-party, but essentially for the next 3 lectures, I will just focus on two parties. Okay, so let's look at the definition. So our definition is heavily inspired by the definition of zero knowledge proofs. So recall that in zero knowledge proofs, we required the existence of a PPT simulator. The simulator doesn't get any input. Simulator doesn't have the witness, doesn't have any secret information, and yet the simulator is able to produce the entire protocol transcript, right? And this sort of captures the fact that the protocol transcript has no information. So in secure two-party computation, protocol transcript does have some information, which is exactly the output of the protocol, right? So a natural sort of idea would be that simulator takes the output of the protocol, and using that alone, the simulator will be able to produce the entire protocol transcript. So that will be our starting intuition. Okay. So our protocol is we have two parties, P1 and P2. With inputs x1 and x2. Okay. And maybe let me back up a little bit and talk about the format first. So the format is that P1 and P2 run a protocol. Let's give some name, maybe let's say protocol pi. With x1 and x2 respectively. And note that the protocol pi might be randomized. In other words, the protocol pi is PPT, probabilistic polynomial time. Now we have two requirements. So first requirement is, of course, the completeness requirement. And here for some function f. And by the way, f must be a polynomial time function. Okay, you can think of f as a circuit. Completeness requirement says that if P1 and P2 are honest, then both of them learn f of x1 comma x2 at the end of the protocol. This is very natural. Now let's try to look at the security requirement. So as I mentioned before, the intuition is we will require the existence of a PPT simulator. There should exist a PPT simulator which takes as input the function output, okay, and which takes as input the function output, but not but the simulator doesn't know the input of the honest party. Okay, let's call this simulator S. S outputs a protocol transcript. Let's call this tsim, such that tsim is computationally indistinguishable from treal. Treal is the transcript of the real interaction. This is very similar to zero knowledge. But there are many questions here, which is why this is just the intuition. First of all, what does it mean to say the function output? Function output on what? The natural interpretation is function output on the inputs x1 and x2, right? But suppose the party P2 is dishonest. So in that case, P2 might have any arbitrary strategy, right? In particular, P2 may not even have an explicit input in mind. Maybe P2 has two different inputs or multiple inputs, and maybe P2 is running some sort of weird strategy, which is some sort of combination of these inputs. I don't know, right? Just arbitrary code. It's hard to say what input it is using. So this term is not exactly well defined what the function output here means. So we need to formalize this definition a little bit further. So this is our final definition. And we will have two separate definitions, one for the case when P1 is corrupt, other for the case when P2 is corrupt. So here the definition is, let's start with the case, say P2 is corrupt. So let's denote it by the party P2 star, some arbitrary PPT strategy. Now, the simulator S is given the code of P2 star. So simulator just has the code of the adversary. S has access to an output oracle. Now S can query, let's call the output oracle O. S can query O on any input x2 star of its choice, and S receives f of x1 comma x2 star. Okay. So output oracle already has the input of the honest party x1. And then finally S outputs some transcript tau, let's say sim, such that tau sim is computationally indistinguishable from tau real. Okay, so one way of interpreting this is adversary can learn the function output on exactly one input of his choice, which is x2 star here, nothing more from the protocol. Any questions about this? And what about the case when P1 star is corrupt? Well, it's the strategy is similar. If P1 star is corrupt, then the simulator can query the oracle with any input x1 star and then get the output. So S gets from the oracle f of x1 star x2. And then the simulator S has to produce the protocol transcript. Okay.
So can you explain once why, like, the first definition means that like the adversary can only find out the output of x2 star? Like, I did not understand that one.
Okay. So what is the information which the simulator has, or
F of x.
which the simulator receives? The only information which the simulator works with is this f of x1 comma x2 star.
Right.
And if using this information alone you can produce the protocol transcript, that means that the protocol transcript cannot have any information other than this. So this is very similar to zero knowledge. In zero knowledge, simulator started with nothing and produced the protocol transcript, which meant that the protocol transcript had no information. Here, the simulator starts with this little piece of information, and the simulator produces the protocol transcript, which means that the protocol transcript has nothing other than this.
Okay. Okay.
Any other questions?
And shouldn't our simulator also consider the case when both of these are corrupt?
No, then whose security are you protecting? So the
Okay.
main point of the simulator is to show that the security of the honest party is protected, that the adversarial party doesn't learn anything about the honest parties. If all the parties in some protocol are corrupt, we don't care about any of them. We don't need to show any security for anybody, right?
Okay. Thank you, sir.
So same, for example, in key exchange, like we never consider the case when both Alice and Bob are corrupt. In zero knowledge, we never consider the case when prover and verifier are corrupt. So this is a general pattern in cryptography. And when we will look at secure multi-party computation, there are n parties, and then up to n minus one of them can be corrupt. And then we want to argue that the security of the remaining honest party is still intact. So that's generally how sort of our thinking is.
So, sir, I have one last question. Like the definition says that S can query the oracle on any input x2 star and receive f1 x1 comma x2 star, right? But
Mhm.
like the only input to S is f of x1 comma x2 star, right? Like,
Mhm.
what does then that mean exactly? Like,
So we want the simulator to be able to choose the input x2 star. and then get the output corresponding to that input. You cannot expect that you give the simulator the output of the function f on some input, and the simulator will be able to produce the protocol transcript, because maybe the input which the adversary chooses in the real world is different from that.
Okay, so you're saying the simulator can produce the transcript for any x2 star.
Yeah. And the
Okay.
simulator queries the oracle exactly once, not more than once.
Okay, and like nobody gives x2 star basically to the simulators.
Nobody gives x2 star. Simulator has to look at the code of p2 star in some sense, and simulator has to learn what x2 star is.
Okay, thanks.
So even though this is a nice definition, let me put a disclaimer here that you shouldn't immediately go ahead and start building software and so on. This is still sort of not the best possible definition. There have been stronger definitions in the MPC literature, but this is probably the simplest, so this is what we'll work with. Now let's look at a generalization. So far, we only looked at the case where all the parties get the same output. Now, what about the case when different parties are supposed to learn different things from the protocol? So that's also possible. So in generalization, we have two functions f1 and f2. Okay, p1 and p2 learn f1 of x1 comma x2 and f2 of x1 comma x2 respectively. Okay, as an example, think about the client server setting. Maybe the client doesn't learn anything, and maybe the server doesn't learn anything, and only the client learns something from the protocol. And in that case, one of the functions f1 can just be bought. It can have zero output. And of course, we can generalize all of this to more than two parties, but we will not worry about that right now. So our goal will be to construct secure two-party computation for any function, for any polynomial time function f. And by the end of the last lecture, the third lecture of the series, we will learn how to do that. Today, we will learn how to run secure two-party computation for simple functions. So we will consider two types of adversaries. In cryptography, generally we think of adversaries as like arbitrarily bad. They can have any code. They just need to be PPT, but other than that, they can do whatever they want. But here, as a stepping stone to make our life easier, we will consider nicer type of adversaries. And they are known as honest but curious, and also known as semi-honest adversaries. And our first goal will only be to construct protocols which are secure against honest but curious adversaries. So what are honest but curious adversaries? They follow the protocol instructions completely, right? You tell them to generate two random numbers. They will honestly generate two random numbers. You tell them to add these numbers, they will add these numbers and send you the sum and things like that, right? So they don't deviate from the protocol instructions, but they are curious. They are curious about what your input is, right? So if the protocol just sends the input of one party to the other party, these adversaries are not going to close their eyes, right? In that case, they do learn your input. So these adversaries choose a good random tape and follow all protocol instructions. But they can analyze the information which they learned. Okay, one way of thinking about it is that maybe during the protocol, these adversaries was completely honest. And then after the protocol terminated, the adversaries became completely corrupted. And then they can take the entire protocol transcript, they can run any arbitrary computation on it to learn something about the input of the honest parties. And we will mainly try to construct protocols for these type of adversaries. And then later on, we will see how in sort of a magical way, you can use zero knowledge proofs to also get security against arbitrarily malicious adversaries. Let me call these fully malicious adversaries. These type of adversaries can use bad randomness. You tell them to flip a random coin. They use some arbitrary non-random string. They can send arbitrary messages. The only restriction is that they have to be probabilistic polynomial time. Okay, so for now, let's focus our attention on this honest but curious. Let's assume that other type of adversaries don't even exist right now. Okay, great. So we are ready to get into our first secure two-party computation protocol. And we will use trapdoor one-way functions or one-way permutations. Trapdoor one-way permutations. And if you remember, we have already seen these objects, and we also saw how to build trapdoor one-way permutations using RSA. Okay, so let me remind you what they are. A trapdoor one-way permutation is basically just a one-way permutation, except that there is also a trapdoor T. If you have that trapdoor, you can invert the one-way permutation in polynomial time. So to recall maybe the relevant part of the definition. So here we have a collection or a family of functions f. We have the ith member of the family going from the domain to the range. and I is in some family I. So this is a family of trapdoor one-way permutations if the following properties hold. So first, we needed a function sampler. So this is a polynomial time algorithm which allows you to sample fi, I, and some trapdoor t. Okay, as an example in RSA, the trapdoor is the factoring of the number n which you choose. And then there is an input sampler. Input sampler allows you to sample from this domain di. Okay, the third property is hard to invert, right? If I give you my function fi, if I give you the output on some random input, it's hard for any PPT adversary to be able to invert it. And then finally, perhaps the most interesting property is the property of invert with trapdoor. Okay, so given t and given fi of x such that x is sampled from di, it's actually easy to compute the input x. And remember, we are talking about permutations. So given the function output, there's only one possible input. So we will use trapdoor one-way permutations to construct what is known as oblivious transfer. Oblivious transfer is a secure two-party computation protocol for a special function f. And I will define the function as follows. So we have, in oblivious transfer, we have a sender. Let's call the sender to be Alice. And then we have a receiver. So sender has two different inputs. Let's call these inputs x0, comma x1. And then we have a receiver. Receiver is Bob. Having input B. Okay. A doesn't learn anything from this protocol. The output of A is bought. Output of B is X sub B. So what is going on? I am the sender. I have two strings. You are allowed to pick and learn any one of them. You don't learn the other string, and I don't learn which string you chose. Okay. So the bit B is hidden from the sender A, and the bit XB bar is hidden from the receiver B. Okay, is the functionality clear? And we will try to design a secure two-party computation protocol for this function. Okay, so oblivious transfer is also just denoted as OT. OT is the most fundamental functionality for secure two-party computation. And now we will see how to build OT for honest but curious adversaries. And we will use trapdoor one-way permutations. And we will also end up using hardcore bits. It's a one-way permutation, so obviously it has a hardcore bit associated with it. So our protocol will run in 3 rounds. So in the first round, the sender A samples some function, let's just denote it as f, and it gets the trapdoor T and sends f to B. Okay, Alice keeps the trapdoor as a secret. So A did not use the input at this stage. The input is x0, x1. Now the receiver B chooses x from the domain of the function f. And B sets y of B to be f of x. B samples y of B bar from the range. So just can think of it as a random group element for the case of RSA. Now B sends these 2 strings, y0, y1 to A. So here what is going on? B chose 2 strings such that it knows the trapdoor or it knows the pre-image of exactly one of them. So A receives these 2 strings y0 and y1. A has no idea whose pre-image is known to B and which string was random from the beginning. So anyway, A has the trapdoor, A inverts both of these strings. Okay, so A computes and sends Zi equals, let's see, xi XOR the hardcore predicate of f inverse of yi for all I in 0 and 1. So essentially, A recovers the pre-image of both of these strings. A has the trapdoor, A recovers the pre-image of both of these strings. And in some sense, A encrypts the input bits using these 2 pre-images. And I should mention here that these are really just bits. Okay, so this represents the preimage of yi, and this is the hardcore bit of the preimage, and you are just using one-time pad now to encrypt xi. And that finishes the protocol. How does B recover the output? B computes h of x and recovers xb as zb xor h of x. So B only has one of the pre-images, and we can compute the hardcore predicate of that one and recover just one of the 2 bits. B doesn't have the other pre-image. B cannot invert the one-way permutation, and hence B cannot compute the other bit xb. The hardcore bit is essentially uniform.
Sir,
Yeah.
so isn't F inverse yi xi itself, and like aren't we going into like circles then, like we are using the hardcore predicate of x to hide x?
Mm. So the point is, okay, let me give some more explanation here. So maybe let's take an example. So say B was equal to 0. Okay, so then B has y0, which is equal to f of 0. Y1 is, sorry, f of x. Let me call it x0. Y1 is uniform, and say y1 equals f of x1. So here x0 is known to be, but not x1. So remember that B is honest but curious. B only has one of the pre-images. Now B gets x0 XOR h of x0 and x1 XOR h of x1. So clearly B has x0, so B can compute this hardcore predicate. B can recover. Wait, am I overloading notation? Yeah, so I should not, x is the input, so I should call it something else. Let me call it r then. Well, here it's fine, but let me change to r anyway, everywhere. So let's look at this value. yi and xi are unrelated. Yeah, that's true. So let's look at this value here. You only have, B only has f of R1. And we have a guarantee that given f of R1, hardcore bit of R1 is supposed to be uniform. And hence this is a one-time pad for the receiver B. Right? Does that make sense?
Yes, sir. Yes, sir. Now I understood. Thank you. Thank you very much.
Anyway, we haven't even looked at the security proof yet. Any questions? So what happens if B is fully malicious? If B can deviate from the protocol? Is there a strategy for B to learn both the bits?
Yeah, if like B like samples X1, R1 and not Y1, then like B can compute H of R1 and then find out.
Yeah, exactly. Good point. Yeah, so it's easy for B to pick two strings y0 and y1 such that B knows the pre-image of both of them. And if that is the case, B can learn both the bits. Right? So we are in some sense trusting B to be nice to us, follow the protocol, and only know the pre-image of one of the two random strings which he sent. Okay, that's fine. That's good enough for us. So we will only try to prove that this is secure against honest but curious adversaries. So completeness here is easy to see, and let's try to argue the security. So we will consider two cases. Case 1 when A is corrupt and case 2 when B is corrupt. And we will have to construct two different simulators. So case 1 is A is corrupt, and in that case we will call it A star. So the simulator works as follows. Step 1, the simulator runs the adversary A star, and S receives F from A star. As the second step, S just sends y0 and y1, where y0, y1, they are both sampled from the range. So A star is not even going to notice, right? A star just expects two random strings from the range, and which is exactly what the sender sends, or the simulator. So note that S doesn't have B, right? So S cannot follow the second step of the protocol honestly. And then A star responds. S just outputs the whole transcript, tausin. So there's no rewinding, nothing. No trying multiple times. This protocol, the oblivious transfer protocol, as we discussed, it unconditionally hides the bit B. So simulator doesn't have to do any funny business. And note that the simulator S did not even use the oracle. And in fact, it doesn't even make sense for the simulator to use the oracle in this case, because the adversary A star receives no output in the protocol. Now let's look at the second and the more interesting case where the receiver B star is corrupt. So now simulator has to start the protocol. Okay, and here S, the first message is honest, S just samples F and T and sends F to B star. Okay. And remember that B star is semi-honest. So B star responds with Y0 and Y1. And here's the key point. S observes the input B from the code of B star. So B star is honest. It's the honest code, right? And when I look at the honest code, I can see, right? I can see which input is inbuilt in this honest code. If it was a dishonest code, maybe it's completely obfuscated, written in some programming language which I don't understand. So maybe that's a problem. But dealing with honest but curious adversaries is much simpler. So now the simulator S has the input B of the adversary. But note that S doesn't have X0 and X1, which is the input of the honest parties. And now S sends B to the oracle and receives XB, which is the legitimate output for the adversary B star. But note that the simulator doesn't get the other input, which is XB bar. So how does the simulator compute this third message? And the idea is as follows. So simulator sets ZB to be XB XOR H of F inverse of YB. Okay, and simulator sets ZB bar to be some, let me say some random bit R XOR H of F inverse of YB bar. So here the simulator used the correct input. Here simulator used some random input. But now the idea is that the adversary B star is not going to be able to distinguish between the case where R was used from the case where the legitimate X B bar was being used. And this is because of the property of the hardcore bit. The adversary B star is not going to be able to decrypt this one-time pad. So you can encrypt any message. Even if you don't know the message, it's not going to matter. So this is essentially the end of our security analysis. And I will not go over the hybrid argument, but in the hybrid argument, so what is the difference between the real transcript and the simulated transcript? The only difference between real and simulated is just in how this message is constructed. In the real transcript, this message has the correct bit of the sender. Here we are putting a random bit. But anyway, hardcore bit says that it's indistinguishable from a random bit anyway. Okay, any questions?
Sir, one small question. For case one, right? Like in our transcript, won't we need to output the like functions like X, which output of A, which is nothing like, or the transcript will only have the messages?
No, the transcript will only have the messages.
Not the final output also like that. Like
Well,
basically,
the final output of A star is just
nothing, that is fine. But
yeah.
for the simulator, shouldn't the simulator also output the thing that like it had to know? XB basically.
No, so the idea here is that you are looking at what A star learns. So
Okay.
you only have to simulate the view of A star.
Okay, so basically, like we don't have to output our side.
Yeah.
Okay.
And here this simulator shows that you can simulate the view of A star given nothing, which means that the protocol is zero knowledge to A star, which means
Okay.
that the output of A star in this protocol is bought.
Thank you, sir. Thank you.
So what we learned so far is known as 1 out of 2 OT. In 1 out of 2 OT, the sender has 2 strings, the receiver learns one of them. But there's a generalization which is known as 1 out of N Oblivious Transfer, 1 out of N OT. In 1 out of N OT, the sender has N possible bits. Let's call them x1 to xn. And the receiver has an index from 1 to n. And let's call this index I. And the receiver is only supposed to learn xi and nothing else. So can we construct 1 out of N OT using same or maybe similar ideas? So here A has x1, x2 up to xn. The input of B is I from The output of A is what as before? And B learns xi. So any ideas on how to construct one out of NOT?
So can we do something like this, that like we represent I as a n-bit message, and like zeros and ones we learn each of them through separate rounds in the protocol?
Well, the receiver B only learns a single bit, right? Which is xi.
Oh,
So all of these are still bits. So this is a relatively minor change in our previous protocol. So as before, A samples F and the trapdoor, and sends the function F to B. So in 1 out of 2 OT, B was supposed to choose 2 strings and know the preimage of only one of them. And now we will just ask B to choose n different strings, but only know the preimage of one of them. So B samples X and sets yi to be f of x. Yj is sampled at random from the range if j is not equal to I. And all these y's are sent across. And A stands for all I. Zi, which is defined as xi xor h of f inverse of, let's see, x y I. Okay, so if you know the preimage of yi, you can recover xi. And B only has one of the preimages, so B only learns one of the bits. The remaining n minus 1 bits are hidden in some sense. So just one more thing, one more generalization, and we will see something really nice. So far we have only dealt with bit OTs. Let's try to go to string OT, where A has x1, x2 up to xn, where these are elements of 0, 1 to the power, let's say some k. Or let me call it L. Okay, B still has the same I from 1 to n. So how can we construct a 1 out of n string OT? And here basically the idea is what Rohan was pointing out earlier. So so run 1 out of n bit OT L times. So this is very simple, right? When you run it for the first time, the receiver learns the first bit of xi, then the receiver learns the second bit of xi, and so on. Okay, so in jth invocation, input of A will be the jth bit of x1, the jth bit of x2, and so on, the jth bit of xn. The input of B remains the same in all invocations. So in the jth invocation, B learns the jth bit of xi. Okay, great. So we have constructed 1 out of n string oblivious transfer. The sender has n strings, the receiver learns exactly one of them, the chosen one. And now let me try to argue that this is really powerful. I have already constructed a secure two-party computation for most functions. In particular, this already gives a secure two-party computation for functions f where one of the inputs is small. By small, I mean it only has a polynomial number of possibilities. Okay, as an example, say A has x1 and x1 can be arbitrarily long. And then B has x2. X2 is not very long. X2 is, let's say, either 1 or 2 up to n. And you can take any arbitrary function, f. Now the secure two-party computation protocol is as follows. So 2PC protocol to get f of x1 comma x2. So party P1 or Alice will act as the sender. Bob will act as the receiver. So the sender A sets so since I'm using x1 and x2 here, let me not use, or maybe let me change the inputs here. Let me call the inputs A1 and A2, and you are trying to compute f of A1 comma A2. So A sets xi to be f of A1 comma I. For all I. Okay, so A starts with some input A1, and A has to run an oblivious transfer. So A computes the inputs for the oblivious transfer protocol as follows. Xi is f of A1 comma I. And B sets I to be exactly equal to A2. Okay. A and B run one out of n string oblivious transfer on x1, x2 up to xn and I. This is the input of A and this is the input of B. At the end of the protocol, B learns xi. Okay. Now, what is xi? Xi is actually supposed to be equal to f of A1 comma I, which is actually supposed to be equal to f of A1 comma A2. So B has received the function output on the inputs A1 comma A2. Okay. So at a very high level, the intuition is that if one of the inputs is small, let's say only n possibilities, then once you fix A1, there are only n possibilities for the output. Okay. So A already knows, hey, these are the n possibilities, output is going to be one of them. Right? I don't know your exact input, but I know that the output is from this list of n inputs. Okay. So then I just prepare this list of whole n possible outputs, and then you download the correct one using oblivious transfer. And I, as the sender, have no idea which output you downloaded. So all other outputs are hidden, which means that the only thing that the receiver learns is just the function output, nothing else about my input. And the sender doesn't learn anything in the protocol at all. So now let's come back to the Yao's millionaire problem. And we have already solved this problem. The only assumption is we have to assume that the net worth of at least one of the millionaires is polynomial. Well, of course, it's, in fact, your net worth is a constant. It's never going to be more than, let's say, 2 trillion or even 1 trillion, right? Even the richest person in the world is worth like $150 billion. So we have an upper bound on the net worth. And then we can construct this huge list, which will have, let's say, 1 trillion element, still polynomial time, though not very, very efficient, but polynomial time, right? So we have built a secure two-party computation for the Yao's millionaire problem. One caveat is that here only B learns the output. What if both parties need to learn the output?
I think they can do the same thing because both of them, their net worths will be bounded, so they can do the same protocol in reverse again, right? The answer will be same.
Yeah, you can do that, or an even easier option is, because we are assuming honest but curious, we can just ask B to send the output to A. at the end. And we are anyway assuming that B is not going to lie. Okay, so we have secure two-party computation for the case where at least one of the inputs is small. So here I considered the possibility where the input is from this list, but you can take any polynomial size list. And now there are many open questions, which we'll look at in the future lectures. So what about, for example, malicious adversaries? That will be the topic of the next class. What about more general functions where both of the inputs can be very long? So as an example, like imagine two huge databases, and you're trying to maybe run some sort of machine learning algorithm on these two databases. So surely, you cannot enumerate all the possibilities for these databases. That will be exponential. So yeah, so we will look at both of these problems in the future lectures.